Okay, we're going to go over the exam. So hopefully this will answer any questions you might have. Starting with question 1, a substance that cannot be broken down into a simpler substance via chemical change is called an element. Compound is 2 or more elements bonded to each other via chemical reaction or change. We can simplify that. We can take H2O into just hydrogen and oxygen. Homogeneous and heterogeneous mixtures, those are even easier to separate into simpler compounds. We can filter them out. We could boil off one. We could carry out a chemical reaction to reduce that to an element. But with an element, there's no way chemically to make that any simpler. If I've got iron atoms, then I'm just going to have iron atoms. I can't take them into something simpler. List the basic steps of the scientific method in the order they must be carried out. So first you're going to have to make an observation, notice something, some change, something interesting, derive a hypothesis from there. Why do you think that is that it happened, or what is the reason for that? Prediction, and then set up experimentation to test that, and eventually derive a conclusion. You may have to do additional experimentation, but eventually arriving at some conclusion. So answer A there. Your morning bowl of breakfast cereal would be an example of, this is a mixture, and in this case, it would be a heterogeneous mixture. If I have a bowl of breakfast cereal in regard to, it depends on where I sample that from. If I sample it from one side of the bowl or the other, or the top or the bottom, I may get, more flakes in one sample than another, or more raisins in another, or more milk, or more air. So that's a heterogeneous or non-uniform mixture. All right, converting 77 degrees Fahrenheit to Kelvin. Let's go to the whiteboard. All right. So I've got 77 degrees Fahrenheit. Probably going to first want to take this to Celsius and then to Kelvin. So to do this, I'm going to divide it by 1.8, the scale difference between Fahrenheit and Celsius, and then I'm going to subtract. Oops, sorry, did that the opposite way. So if I remembered that 32 degrees Fahrenheit is 0 degrees Celsius, that'll make sure I do this in the correct order. So first I'm going to subtract 32 from that, then divide that number by 1.8. So 77 minus 32 gives me 45, and 45 divided by 1.8 gives me 25 degrees Celsius. And then to go from Celsius to Kelvin, I would add 273 or 273.15 if you want. But based on your answers, you're going to arrive at that one right there, answer C. Okay, back to our exam form A, number 5 here. Read the length of the metal bar with the correct number of significant figures. So we need to go out to the estimated digit. So we can see there's 15, 16, and we have multiple tick marks. So we have a tick mark every 10th place. So our certain digit would go out to the 10th place, or one digit after the decimal. And then our estimated digit would go one additional place beyond that. So if the last certain digit is in the 10th place, then our estimated digit is in the 100th place. And the only answer that has a digit going out to the 100th place is D. Classify the change represented in the molecular diagram shown below. You can see, even on your form, you're going to have some white balls, maybe some gray balls instead of red, or spheres. And you can see they're all the same on the left-hand side and the right-hand side. So chemically, there's no change. The elements that are present, what they're bonded to, how they're bonded, is identical from the left to the right-hand side. What you will notice is they're very close to each other on the left-hand side and very far apart on the right-hand side. So we're probably seeing here is a liquid going to a gas, or maybe a solid going to a gas. So evaporation or sublimation, that would be a physical change, but not a chemical change. Chemically, it's the same. So this would be B, physical change only. The factor 10 to the negative 6 corresponds to which prefix? 10 to the negative 3 is milli, 10 to the negative 6 is micro, 10 to the negative 9 would be nano, So this would be D micro. So if this was, 1 times 10 to the negative 6 grams, that would be 1 microgram. Which of the following are examples of intensive properties? So intensive properties are specific to that material, and it does not matter if we have a lot of this or a little of this, that intensive property will not change. The only one out of all of these that is intensive would be density. If I have a small piece of copper or a large piece of copper, the density is the same. Whereas mass, volume, weight are dependent. They're all extensive properties. They're dependent on how much of that thing we have. Small metal cube, here, let's go back to our whiteboard. Got a small metal cube, has a mass of 128 grams, and its length, width, and height are all 3.05 centimeters. So we have a list of densities on our last page. So we should have enough information here to find our density. Let's take our length, width, height, and multiply them all by each other, or we can cube that 3.05. That should give us 28.373 cubic centimeters. And to find density, we want grams over cubic centimeters. So 128 divided by 28.373 gives us 4.51 grams per cubic centimeter, or a density of 4.51. And if we look at all those density values on the last page, we see the one that this matches is titanium, or in this case, answer A. All right, now we have a significant figure problem. So we have 965.43 times 3.9110. And then from there, we're going to add 9,413.4136. So I'm going to carry out the portion in the parentheses first. And that gives me 3,775.79673. Now, technically, so we did the operation here we did was multiplication, and the rule for that is the least number of significant figures. 965.43 has 5 significant figures, 3.9110 has 5 significant figures, so they each have 5 significant figures. The minimal number, or then the number of significant figures our answer here is going to have is going to be 5. So 3,775.7, that's where we would stop. If we were all done, we would round that. That would end up with 0.8. But because we're in the middle of the problem, I don't want to do any rounding yet. So I'm going to note how many of those values are significant, but I'm going to keep that entire number. And to that, I'm going to add 9,413.4136. When I do that, I get 13,189.21033. Now, the last operation that I did was addition. The rule for addition is the least number of digits after the decimal. This, actually, let's go with a different color. This has 4 digits after the decimal. This only has 1 significant digit after the decimal. So that means we're going to take this and we're going to go out and stop at 1 digit after the decimal. So that gives us 13,189.2 based on our rules for significant figures, multiplication, division, etc. All right, student performs experiment to determine the density. So they get these values, 1.72, 1.74, 1.78, and 1.75. Let's make that better. So our true value is 1.75. So we need to find out how wide a range do we have, and what is our average value to figure out if we're precise or accurate or neither. Our range here, so from 1.78, our largest number, to 1.72, our smallest number, gives us a range of 0.06. If we take our range and we divide it by our average value here, actually, let's do our average value first. So if we add up all these, if I take 1.72, I add 1.74, and I add 1.78, and I add 1.75, I get 6.99. That's 4 values, so divide by 4, and I will find the average value, 1.7475. So our range, that range of 0.06 over our average value, gives us a range of about 3.4%. I believe in class I said if the range was less than 10%, you could consider it precise. And then our average is 1.7475. So this is even less. This is 0.14% away from our average. So I said if we were within 10% of our average, that would be considered accurate. So that's why this is both accurate and precise. The values are very reproducible. They're very close to one another. And their average value is very close to the true value. True compounds consist of nitrogen and oxygen are decomposed. Sample 1 gives us 11.1 grams of nitrogen and 14.2 grams of oxygen. So that we get a nitrogen to oxygen ratio of 0.7816. And our second sample is 16.4 grams of nitrogen for every 10.5 grams of oxygen. And that gives us a range of, or sorry, a ratio of 1.5619. They're not the same ratio, so they must be different compounds, both containing nitrogen and oxygen. If we take the ratio of nitrogen to oxygen in one compound and we put it over the other, we get 1.99, or really about 2. So we have a whole number ratio of nitrogen and oxygen in sample 2 compared to sample 1. So this is why this would be the law of multiple proportions. Let's see. Next one tells us that if we have a sample of lithium bromide, no matter how much we have, where it comes from, if it's a small sample, a large sample, if we collect 9 samples, we're always going to end up with a ratio of, 7.99 to 92.01. However you want to write that. So since we have a fixed proportion for this particular substance, that's the law of definite proportions. Now we're not looking at 2 different types of samples, but just one specific lithium bromide compound. And because that ratio is fixed, that's a definite proportion. All right, now we have another sample. We decompose this magnesium fluoride And for 1, we get 2.57 kilograms of fluorine for every 1.65 kilograms of magnesium. And this ratio here is fixed. Whatever this compound happens to be, because of the law of definite proportions, we're always going to have a fixed ratio of fluorine to magnesium. So we can use that ratio, multiple different ways we could kind of write this out or set this up. I'll do it like this so you can see the units, but now we're told we have a second sample, and we don't know how much fluorine's in it, but we do know how much magnesium's in it, and since that ratio is fixed, I could multiply our ratio by how much magnesium we have, and that will give us the amount of fluorine we would expect to find in that second sample. Identify the number that contains 5 significant numbers. So we have 3, 1, 5, 4, 8, 1, 8, 9, 1, 0, 0, 7.4210, and 7.003 times 10 to the third. This one has a leading 0, so that is not significant. So we would only look at these values. That would have 4 significant figures. This has 5 values, but those last 2 are what we would call ambiguous. Ideally, we would put a decimal in here somewhere to make them non-ambiguous, or rewrite them in scientific notation, which again would include a decimal. But we'd really say 3 sig figs or maybe ambiguous. All digits after a decimal are significant, including the zeros. So this would have 5 significant figures. This would only have 4. And that's why this would be our answer if we're looking for 5 significant figures. I think some other versions ask for a different value, but all the rules would apply in the same way. Which of the following statements is false? There we go. So we're on 16, which is false according to Dalton's atomic theory. Atoms combine into whole number ratios to form compounds. That's part of Dalton's theory, again, that we can't break the atoms up into something smaller. So I have to have 2 hydrogens for every oxygen for water, or 1 hydrogen for every oxygen for hydrogen peroxide. Atoms of chlorine have identical properties that distinguish them from other elements. Yep, 1 chlorine atom should have all the same, physical chemical properties of another chlorine atom, and be different and distinct, say, from a carbon atom or a fluorine atom or whatever. 1 carbon atom will combine with 1 oxygen atom to form a molecule of carbon dioxide. So again, there's our definite proportions, whole number ratio combinations, that fits that. And D, an atom of nitrogen can be broken down into a smaller particle that will still have the unique properties of nitrogen. Nope, according to Dalton's atomic theory, atom's the smallest representation of nitrogen that we can get that still has its properties. So that's why D would be the false statement there regarding Dalton's atomic theory. Here we go, back to the whiteboard. So now we have crate. It is 2.22 meters by 2.22 meters by 0.712 meters. It's filled with water. We want to know how much it's going to weigh. And we looked at where we have the density of water there on that last page. It's 1 gram per milliliter. A centimeter cubed is the same volume as a milliliter. So what I would probably do is convert my units here into centimeters. So 100 centimeters in a meter. So we'd have 222 centimeters times 222 centimeters times 71.2 centimeters. If I multiply the length, width, and height by each other, should get 3,509,020.8 cubic centimeters times the density of water gives us the same value in grams, 3,509,020.8 grams, and we wanted this in kilograms, so I can divide by 1,000, or I could set up my dimensional analysis. It's going to give me 3,509.0208 kilograms. I could, in this case, my measured values all only have 3 significant figures. We did multiplication to get all this, so my final answer should only have 3 significant figures. And the options there that present themselves are written in scientific notation, would look like that. Identify the unit of measurement, SI base unit of measurement. So here, our options are the yard, Kelvin, tablespoon, or pound. Yard, tablespoon, pound are all different English units. The only SI or base unit here is Kelvin. Which of the following is an example of a physical property? So a physical property is where it would maybe change states or something like that, but not change chemically. So carbon monoxide being poisonous, this is a measure of its reactivity. It's a chemical property. An iron nail rusting, how does it react with oxygen? And it changes it chemically. That's a chemical property. Ethanol melts at 159 Kelvin. Ethanol goes from a solid to a liquid. It doesn't change chemically, it only changes physically, so B would be the physical property. And last, rewrite 0.00265 in scientific notation. So the easiest way to do scientific notation, we have to remember we're going to keep 1 digit to the left of the decimal. So I want to rewrite 0.00265 as 2.65. In this instance, I'm going to move the decimal 1, 2, 3 places, and it's moving to the right as the number is very small. So this would be a -3. Other versions had, I believe, 3 zeros. In those version of the exam, you would be moving this 4 places. So the scientific notation for those versions of the exam would have been to the -4. That should be everything. If you have any questions, feel free to reach out to me. You can email me, you can stop by office hours. Otherwise, I will see you Wednesday.